I wanted to make a video to address some of the questions you guys handed in when you gave me your LB graphs and your graphs of the formation of product over time. And this I just took from one of the submissions. I just wanted to show that to you because A, it's beautiful. Thank you to the student who made it this gorgeous, but also to reorient ourselves. So this was the activity we did in class, and the final point was to get your data so that you can plot it on an LB plot. So 1 over substrate concentration over, versus 1 over initial velocity. And so that was all taken from the actual data that you would gather in a lab where you're calculating initial velocity from the formation of product over time. So one of the first questions that I saw was how to use which graph. So the two graphs that we went over in terms of Michaelis-Menten were the Michaelis-Menten graph where substrate concentration is plotted against initial velocity for each of those substrate concentrations that you used. And so if you want to get Km of your enzyme from these data points that you've gotten in the lab, you can only guess at what Vmax would be because Vmax is the line that this curve is approaching. Where do you exactly draw that line? You're not sure. So you can't get Vmax eyeballing it from this graph. And if you can't get Vmax, you can't get Km. But if you are told what Vmax is, you can draw that line with complete precision. And once you know that number, Km is the substrate concentration at 1/2 Vmax, and you know the exact number for Vmax, so you go to that point on your graph and you can read Km from it. So you'd find wherever 175 is. I mean, granted, this would be on graph paper, so you could do it with precision. And then the substrate concentration that corresponds to half maximum velocity is right there. So you can use this graph if you're given a Vmax to then get a very good estimate of your Km. But if you're not given the Vmax, then you have to take matters into the Lineweaver-Burke plot land. So then each of the data points that you have that made this original Michaelis-Menten curve, you take the inverse of them and you plot it on the graph. Draw your best fit line, and then you can read your intercepts. Oops, that should be 1 over Vmax, and this is -1 over Km. You read those intercepts off of your graph, and then you can calculate your actual Vmax and Km. So that's when you use one graph versus the other. Another student asked, when do you use the Michaelis-Menten equation, and when do you use the Lineweaver-Burke plot? So the Michaelis-Menten equation is initial velocity equals Vmax times substrate concentration over Km plus substrate concentration. If you're not given Km, or sorry, I should point it there. If you're not given Km or Vmax, and you don't have a way to calculate Km, you have no way to derive Km or Vmax mathematically, like let's say, like in the practice problems, you are given Kcat and total enzyme concentration. Well, then you can calculate Vmax, and if you don't know Km, you can solve for Km. But if you're missing both of those values, you can't solve for either one, you have two unknowns and you can't use the Michaelis-Menten equation. So remember, with algebra, you have to have just one unknown. And if you're not given enough information, you can't use the Michaelis-Menten equation. So that's when you use the equation, is you're given all info in the equation, or the means to calculate it somehow, except one unknown. Because otherwise you can't use that equation. Now the LB plot, you can do that if you're given a bunch of substrate concentrations and the initial velocity that is associated with each of using each of those substrate concentrations. You can take the inverse of all those points, plot it on an LB plot, and get both Km and Vmax from your graph. So that explains using the equation versus using the plot. Another question that came up was about the units. So going back to the student submission, that looks absolutely gorgeous, so I'm using it. The data that you were given, the velocity is the change in product over the change in time. So you're measuring the product, in this case, in micromoles per minute. The amount of substrate you put in, you're told was measured in millimoles. So that doesn't match, but that's not a big deal. That just happens to be the units that were used in the laboratory for the measurements. You can just as easily convert all your units to be the same. You don't have to do that because you're not putting them into the same equation to solve for an unknown. If you do put numbers into the same equation like Michaelis-Menten, you do have to make sure all your units match. But for this, the appearance of product was measured in micromolar because that seemed to be appropriate to the researchers. But let's say this 20 micromolar here, you could have easily also have reported that as, instead of 20 micromolar, 0.20 millimolar. I think the reason that it wasn't reported in millimolar is because that's going to be a little bit harder to work with because it's such a small number. You have your decimals, but it's just a matter of taste. So your units don't have to match. You usually pick units that give you numbers that are reasonable to graph with, that you're comfortable with, not too many zeros, not too small. But in reality, you can plot with whatever numbers you want, as small or as big as they are. You could convert everything to molar if you wanted, or nanomolar. So they don't necessarily have to match. The substrate that you put in is something you measure. The product that comes out, it might come out in large increments, it could come out in small increments. So the unit can vary when you decide on how you wish to report the appearance of product. One student said, how did you know to make the graph look like it's increasing when the points are decreasing? So when you take the inverse of your information, your substrate and your initial velocity, big numbers will become small now, right? If your initial number was 50, now it's 1 over 50. If it was 20, it's now going to be 1 over 20, and 1 over 50 is going to be smaller than 1 over 20. So in essence, the order of the data points is actually going to get reversed. But you know what? Don't trip. The order of the data points is irrelevant. Just plot them on the LB plot and draw a best fit line through your data points. They will look like they're quote unquote increasing. Don't trip. I think I'm understanding this person's question right. It's just when you take the inverse of numbers, it's now going to be your points were increasing and now they're going to be decreasing. But the relationship, what's really important is the relationship between a particular substrate and the initial velocity that it created. That's the real important takeaway that you must preserve. And you do that. You just take the inverse and plot your points. One person asks, what am I supposed to get out of this exercise? Always a good thing to ask yourself when you do anything. So what you're supposed to get out of this exercise is to know how to get Km and Vmax from an LB plot. Or if you're given the change in product over the change in time for several time points, or maybe you're given substrate concentration versus initial velocity. In class, we started here and we derived everything else from there, but you should be able to drop in and do this kind of analysis from any point in the process. What else are you supposed to get out of this exercise? More comfort with reading these graphs. And then most importantly, I created this activity because students had mentioned they didn't see an application of enzyme kinetics. I'd give them the lecture on enzyme kinetics and then they'd be like, what is this used for? So giving you an actual data set and having you go all the way to Km and Vmax hopefully adds some meaning to what I talked about in that first enzyme kinetics lecture. Another person asked, what's the difference between initial velocity and Vmax? And one of the reasons actually that I like doing these kinds of activities is then it inspires you and causes you to ask questions like this, which is about the actual content. So initial velocity is going to be the initial rate of product formation when you have a situation when your enzyme is given some substrate. And the more substrate you give an enzyme, the higher its rate of production is going to be. And when we look, if you just want to look at the situation, like how much product is appearing over time, whoops, that should be reversed. As you watch your reaction go, more and more product gets made and then all the substrate gets used up. And so this was that first graph that I showed when I talked about enzyme kinetics. So initial velocity is the slope at the very beginning of your reaction. So that's the initial velocity. This is going to be at a particular substrate. I'm just going to say, let's say it's 10 millimolar. So let's say you give your enzyme even more substrate. So this is 10 millimolar substrate. You're going to get even more product getting made because you started off with more substrate, and so on and so forth. Sorry, that got uglier and uglier, but you see my point. And so with each of these starting amounts of substrate, you're going to have a different initial velocity. So different substrates and a particular initial velocity. Now Vmax is the fastest velocity possible for the enzyme. Now, keep in mind that's going to depend on enzyme concentration. So for this, we're always saying enzyme concentration is fixed. So given a fixed enzyme concentration, what's going to be the Vmax? And that Vmax is what you can see in the Michaelis-Menten graph, where you're plotting what the initial velocity was when you use different substrate concentrations. And you can see the more substrate you give your enzyme, the faster the very first initial velocity is going to be. The velocity will slow down as it runs out of substrate in a particular tube. But each of these data points is a separate tube, same amount of enzyme, but different substrate concentrations. And so you get to a limit of how fast you can go. And the fastest you could go is Vmax, where you are experiencing something called enzyme saturation. Every single enzyme molecule in that tube is going to be bound up with substrate. So adding more substrate isn't going to make the enzyme work any faster. It literally cannot. It has been saturated. So that's how you get to see initial velocity gets higher and higher the more substrate you start with. And if you provide so much substrate that it's like a lot for that enzyme, maybe the initial velocity will be Vmax. So there was a practice problem in which you kind of made that conceptual leap, because they gave you the Km, where it's the substrate concentration at half maximum velocity. And they're saying the substrate concentration was like 1,000 times more. You could assume the initial velocity will be maximum, will be Vmax. And so that's the difference between initial velocity and Vmax. Vmax is the fastest an enzyme goes, and that initial velocity might be there if you have provided enough substrate in the reaction when it starts. Another person asked, could I please explain how you get the point value? And I'm assuming they mean the point value for Km and Vmax. So I'll just do it for Km. When you read the x-intercept off the graph, you saw that it was negative 0.1. So that x-intercept is negative 1 over Km. So you set that equal to 0.1 because that's what the intercept is when you read it off the graph. Then you can cross multiply. I divided both sides by negative 1 to make it all the same, already in my head. And then you got 1 over 0.1, which will be 10, and the units were in millimolar. Another question was, how can we bring Kcat in this context? And so you have the LB plot, and from here you have Vmax and Km that you read off of the plot. Now Kcat is going to be the rate constant for your slowest step. We can't extract that information from the LB plot, but it is related to something in the LB plot. We know that Vmax is equal to Kcat times the total enzyme concentration. So for example, if you got the Vmax from an LB plot and you were told what the total enzyme concentration was, you could solve for Kcat. So the last two questions I see in my pile, one of them asks me about assumption 1 and assumption 2 in the derivations of the Michaelis-Menten equation. I'll make a separate video for that because that is kind of its own topic. And the last question I see is what exactly are the x and y intercepts? So for the LB plot, the x-intercept is negative 1 over Km, so you can use that to solve for Km. And the y-intercept is 1 over Vmax. So you can use that number you read off the graph to solve for Vmax. And they also asked to explain step by step how to calculate Vmax, Km, and half Vmax. Half Vmax, you could, if you're given Vmax, then you just take half that value and you can find it on the Michaelis-Menten graph. But I think I went over the LB plot enough in this, and if you do want to look at more step-by-step information, on Canvas there is a color-coded student graph uploaded, and it does walk you through each one. But the process being, you figure out initial velocity for each substrate concentration that you use. Then you just take the inverse of each. Then you plot the points on the graph, draw your line, and then you go ahead and read your intercepts off of those graphs. Hopefully this helped, and please let me know if you have more questions.